A tree is a collection of nodes that has a hierarchical structure. They can be used for arithmetic expressions, lists, decision trees, file systems, and faster methods of searching, just to name a few. Each item in the tree is referred to as a node and will represent some value. All nodes have parent-child relationships. A parent is located higher than its children in a tree. A parent can have 0 or more children, however each child must only have one parent. So adding an edge between these nodes would break this property, and this would no longer be a tree. The one exception is the topmost node, which is called the root, which will not have a parent. There can be at most one root node in a tree. 2 or more nodes that share a parent are referred to as siblings. Nodes that do not have any children are called external nodes. These may also be called the leaves of the tree. Nodes with 1 or more children are said to be internal. An ancestor of a node is another node that appears higher in the tree along a path. Here, First Street's parent, Dayton, grandparent, Montgomery, great-grandparent, Ohio, and great-great-grandparent, United States, are all its ancestors. In fact, the root node will be an ancestor of every item in the tree. Conversely, nodes that appear lower than another node along a path is a descendant. So First Street is a descendant of Ohio, but it is not a descendant of Greene County. The depth of a node is the same as the number of ancestors it has. Here, Beaver Creek has 3 ancestors, so it has a depth of 3. A tree's height is the maximum depth for any of the nodes, which for this tree is 4. If we take one of the nodes in a tree, along with all of that node's descendants, and then remove it from the original tree and make it the root, we have a new tree. This is known as a subtree. Binary trees have all the same properties as regular trees, except that they may only have up to 2 children per node. Child nodes are labeled as the left child or right child. Left children precede right children in ordering. If every node has either 0 or 2 children, it is called a proper binary tree. Otherwise, it is improper. A proper binary tree, where all leaves are at the same depth, is a perfect binary tree. There are many ways to represent a binary tree. The first is using a linked structure. Each node will provide 4 references. One will be to the actual element at that node. Since this is the root, it points to an object holding United States. Then it has 2 pointers for the left and right children. If a node does not have a left or right child, these will be null pointers. The last is a reference to the node's parent. Since the root does not have a parent, the pointer is null. These 4 references exist in every node in the tree. When traversing a tree implemented like this, we can only move up and down between parents and children, as we do not have direct references to siblings or ancestors above a parent. Another method of representation is to use an array. If we start with the root node located at index 1, then we can store each node's children at indices 2i and 2i plus 1, where I is the index of the parent. Let's build a binary tree using this method to make it clear. We start with the root node and place it at index 1. Now we want to give this a left child. Left children will be placed at index 2i. Since 10 is located at index 1, 6 will be placed at index 2 times 1, or 2. Now, adding a right child, we want to place it at 2i plus 1. 10 is still the parent and has an index of 1, so 3 will be placed at index 2 times 1 plus 1, or 3. Now we add a left child to the 6 node. 6 has an index of 2, so 5 will be placed at index 2 times 2, or 4. We don't want to give this node a right child, so at index 2 times 2 plus 1, or 5, we won't put anything. 3 has an index of 3, so the 1 is placed at 2 times 3, which is index 6. Finally, we put 2 at index 2 times 3 plus 1, which is index 7. Now we have our tree stored as an array, which will make future manipulation and traversal very easy to do.